Hi everyone. So today I wanted to make a recording of a talk that I gave previously this year at the end of summer at the D3A conference in Nyborg in Denmark. So this was a talk in the Programming Languages in Denmark workshop. But I was hoping to reach a wider audience by recording this. So the talk is titled An Invitation to Privacy Problems, and my name is Paul Nelson. I'm an assistant professor at the University of Copenhagen, and I work on mainly privacy, I would say, but also security-related issues, and I work a lot interdisciplinary. So I wanted to spread sort of the joy and interest for privacy across areas, and invite you all to be interested in privacy problems. So let's just jump right into the presentation. So first of all, why privacy? So I'm a privacy researcher, and to me and other privacy researchers, mostly we will just skip this slide and already have all established that privacy is really important. But if you don't work with privacy, why should you care about privacy in the first place? So I want us to think of privacy being important for multiple different reasons. One being that privacy is a legal obligation. So if you look at the literature of privacy as law, you will probably find this paper, The Right to Privacy. It's an old paper written by Warren and Brandeis in 1890. And so these are lawyers writing about how privacy is really important. And if you don't know the paper, I recommend to give it a read. It's really quite interesting to read such an old paper and how they think of privacy. But what really spurred so the reason why they wrote this paper is that actually paparazzis were popping up basically on the streets, and they would take pictures, right? And they would put them in newspapers and write about what people were doing. And Warren and Brandeis were saying, this is not right. This is an infringement on privacy, because all of a sudden people can basically easily document what's happening, maybe even without people knowing that they were being part of a picture, and then they can publish it in newspapers and they can spread gossip, right? So this is a really early example of talking about privacy and how it's important. And I would even say that they basically talk already in this paper about misinformation, because they're talking about how media and journalists and newspaper can spread whatever rumor they want, right? So it's an early example of talking about misinformation. So let's move a little bit closer in time to now, but still quite far away. We have the Universal Declaration of Human Rights. This is written by the United Nations, and it's from 1948. And here we again have, privacy is a right for everyone, right? So that's quite early, and something I think maybe most people are aware of. And then even more closer to today, most of you have probably heard of the General Data Protection Regulation, the GDPR, which is a regulation for how you can collect and handle, process data in the EU. And this is somewhat recent, 2016, so it's more of a modern law of data processing. And so most of you have probably encountered it in some way, either that you maybe had to take some course on GDPR and how to handle data, or that when you go to a website these days, you have all these cookie banners that asks what they can do with your data, if they can gather it or not. And so all these are in sort of like a side effects of the GDPR. And this is Europe centric, right? But there is similar, or at least was similar regulations, for example, in the US, like the California Consumer Act and so on, right? So this is more, a progression of, law cares about privacy, right? So by law, we should somehow have privacy. So I hope that is, a motivation to some of you, but you might also say, okay, well, that's just law, right? But why should I care, and what's the reason? I want to also show you some more like real world examples of, I would say, breaches of privacy. So a lot of the time we will have different data leaks. So here is an example from 21 where data leak, is exposing private records from corporations and government agencies, and this might be a violation to privacy for individuals, but also, as a government agency. So this could be a case of national security at worst if there are sort of basically military secrets leaking, or maybe leaking where people are. If you're a spy, for example, it's not very good that this is leaked. There was also a big breach, the OPM data breach, which was again jeopardizing national security for more than a generation, right? So it's more data leaks, or maybe more, I don't know if it's close to harm, but like it's clear there's a privacy violation, right? When there was a medical data leak in Brazil. So this is from 2020, and it's a lot of people's data. 243 million medical records leaked, and they were available online for 6 months. So who knows how many people have the data now, right? There was this Equifax data breach, was affecting, here it says, nearly half the US population. So they were first saying that might be 143 million people. They even upped that number for 247 million people. So it's a lot of people being affected by their data leaking. And so you can say, well, who knows what will happen once the data is leaked? Who knows if it's, maybe I've got nothing to hide and that nothing bad can happen, right? But sometimes we actually do see fatal consequences linked to these breaches. For example, there's this website called Ashley Madison, and it's very sort of popular for privacy researchers to bring up because it has a very clear privacy implication. So the website itself was like a dating website with people having the intention to cheat. So people who were already in relationships would sign up to Ashley Madison to find someone to have an affair with. And here you can say it's interesting in the sense that what you're writing on the website itself might not even be that sensitive in itself, but the fact that you signed up on the website is sensitive. So just being part of this group of users of Ashley Madison is actually really sensitive. And in this case, the database actually leaked who were users of Ashley Madison. And afterwards, there were 2 suicides that were linked to this leak. So in the worst case, a privacy breach might have these, catastrophic consequences. So I'm hoping that now I've convinced you that, privacy is important, whether you believe that's for the legal reasons or for the implications it can have for people once their data is somehow leaked and, misused in different ways. And so I gave this talk originally in a workshop on programming languages. So I went with first, a broad title of Invitation to Privacy Problems, but really it sort of could have this alternative title, like why is privacy a PL, a programming language problem? And it's basically the way I've designed the talk. It's divided into 2 different sort of parts. The first one being we're looking at, okay, privacy, what is privacy? And the second part being, well, why is it a programming language problem, right? So the talk will be like this, part 1 and part 2 basically, and we talk about privacy and then we talk about programming languages. Okay, so I think a very important question in the context of this talk is, what is privacy even, right? I talked about privacy being part of law and how there were all these data breaches and that somehow being connected to privacy, right? But then what is privacy? And I think it's a really actually difficult question. I've been working on privacy now for about 10 years or so, and I still think this is really hard to define. So one thing that I've been thinking about is privacy and security the same thing? Because a lot of the time we do see privacy and security mentioned maybe in the same sentence, or sometimes in academic context. It's even one of our bigger security privacy conferences is called IEEE Security and Privacy, right? So is it because they are, just fitting together, or is it because that's a synonym, if, it's just the same word, or what is it? So first I was thinking, maybe they are the same thing. But the more I'm thinking about it, at this point, I believe actually they're not the same, but they have similarities. And I would love to sort of, convince you at this point. Otherwise, let me know what are the things you don't agree on. So my claim here is going to be that we understand security. It seems that it's a quite well-defined problem within the community. And I don't think that we understand privacy yet. Right, so this is why I think that they can't really be the same thing, because we understand one and not the other. And to sort of argue further, I'm going to give you some examples. I'm not just going to throw out this claim and leave you with that. I'm going to try to provide some evidence. So if we look at security and privacy, and we look at properties that we want to guarantee, if we look into the literature, if we look at security in a textbook on security, what you will see is usually this CIA, confidentiality, which is secrecy of data, and integrity, which means not being able to tamper with data or change it in different ways, and availability, right, which is that the system is somehow accessible and useful, if you will, because it's very easy for us to just guarantee confidentiality and integrity by simply having a system that, it's not connected to the network, so no one can interact with it, and therefore it's secure, right? So we do really need availability as one of those properties that we want to achieve, to have, systems you can interact with that are useful, right? And basically protecting against stuff like distributed denial of service attacks, that's sort of guaranteeing availability, which is also central in security. So if you look in the textbook, these are the three properties that you will likely see security defined as. And sometimes you might also see that someone adds some extra properties like non-repudiation, where you can't forge someone else's signature, or these kind of properties, right? But the core things will be these three. When it comes to privacy, it's more unclear. And they might either, like you say, that security and privacy are the same, or they might sort of gloss over it. And so it's not clear what property it is. Sometimes it might be a kind of secrecy that we want to hide some information. And then you can sort of say, well, in that case, it's just confidentiality, right? But it could also be that we have in the literature that is coming from philosophy, actually, the concept of contextual integrity. In contextual integrity, it's not necessarily the reasoning about data as being secret or non-secret. It's saying that the context matter for whether data should be shared or not. So an example would be like medical data. Often we will think of medical data as, that is sensitive, that is secret, right? But contextual integrity sort of specifies to whom and when, right? So it would be inappropriate to share my medical data with my supermarket, because I don't want them to know about like whatever diseases I have, right? So I would say that that's inappropriate. And contextual integrity would talk about basically privacy violations as inappropriate flows of information. But my medical data, if it's shared with my doctor, I would think that's appropriate. I would think that, well, this is good because then I can get treatment, right? So in contextual integrity, you're reasoning about inappropriate and appropriate information flows. So appropriate flows, they actually guarantee privacy, and the inappropriate ones are privacy breaches. And they say that that's contextual. So it's sort of on the level of, it can even be on the level of individuals or cultures or settings. It's a quite flexible definition, actually. So is privacy contextual integrity? It's more flexible than just secrecy, because now we're saying from whom is it secret? And there is also the notion of differential privacy. I will touch upon it more later, but in broad strokes, differential privacy is a statistical notion to reason about how much information we are leaking. So usually we're not reasoning about the fact that no information is leaking. We're using it typically when we want to release some data, like we want to anonymize some data, and we want it to be still useful, right? So that's one other definition. And then all of this is also, well, where's the GDPR coming in, right? Because they have some other definition of privacy where they think about personal data and non-personal data. And they define personal data in a specific way of how it relates to people. And then non-personal data is simply the complement of whatever is not personal data is not personal data, right? So that's a completely sort of different take on privacy. But what I'm trying to get at here is that in the literature, there is not really one clear definition of like this is privacy and it's only this thing. It's actually quite different flavors of privacy depending on, you know, what paper you're reading, what context you're in, what sort of community you're speaking to, right? Like in algorithms, a lot of the time we will reason about differential privacy, right? In philosophy, you might think of contextual integrity. You might also think about contextual integrity in human-computer interaction. It's not so clear when we talk about privacy what we actually mean. Whereas security seems very stable to mean some of these properties. All of these properties usually plus some with a well-defined threat model. So what I want to note here is that as I was thinking about this, is I think we're actually sort of comparing apples to oranges, because privacy, I think, is a goal. It's something that we want for people. And security is usually a set of different mechanisms that is used to achieve these goals. So these mechanisms then have these properties. For example, encryption, right? That's a mechanism that can give us confidentiality. And that can be used to achieve privacy if we believe that privacy is secrecy, right? But maybe it's not enough on its own, because maybe we actually want to share some of the data, but not all of the data. And then encryption is not gonna completely solve the problem for us. And even more interesting, that we also have an opposing goal of privacy, which is surveillance. And a lot of the time you can use security mechanism to achieve surveillance. For example, in the security literature, we have stuff like intrusion detection systems. And they are basically surveillance systems, usually of networks and computers, to see if there is a break-in in our system, right? And in this case, we are using security mechanisms to achieve surveillance so that our systems don't get hacked, right? And surveillance of like what we are doing, right? That's the complete opposite of privacy. So there seems to be something interesting happening here with this tension. And I also wanted to add as a sort of another rationale for why do I think security and privacy are different, is that some privacy problems are indeed security problems, so there's an overlap. But I don't think that all security problems are privacy problems. Okay, so that sounds maybe very complicated, so I want to exemplify. So consider this example. Let's say we have a weather station that just collects weather data. Nothing about people, nothing in a private per se, just data that we would anyway report to the public. And now this weather station gets hacked. So someone breaks through the defenses and, you know, changes the password, maybe, you know, deletes the data, changes it, or something, right? Then we definitely have a security breach because someone got into the system that was not intended to have access. But it's not a privacy breach because that did not leak any information about an individual. Like this would not have been personal data on the GDPR, for example. So this is a security breach that's not a privacy breach. But on the other hand, even if I have a similar setting, but instead of this being a weather station with weather data, let's say that it's medical data being stored at a hospital and someone breaches that system. At this point, it's a security breach because someone hacked into the system, right? But it's also a privacy breach because all of that medical data was about people, right? So there is some overlap, and it's kind of unclear how big that overlap is. I don't think that it's a complete overlap between security and privacy, but I do think that there is overlap. And there is also something really interesting about how security and privacy breaches differ. And I wanted to show you this slide. So privacy breaches are forever, just like diamonds. And this slide was actually inspired by a talk I went to with one of the creators of Defense for Privacy. Kobi Nissim had this statement of privacy breaches like diamonds are forever. So what do I mean with that? Well, when there is a security breach, I think that's usually a recoverable state, like with the weather station. If there is a breach, like this was bad, right? Like someone broke into the system with an intent for that to happen. So we maybe changed the passwords of the account that got breached. Maybe we add some extra firewall. Maybe we segment the network. We add some sort of defenses so that it will not happen again, right? And we sort of recover. Similarly, if I lose my credit card, that would be bad for me, right? That someone could just go on and use my credit card and basically steal my money, right? I would call the bank and I would say, hey, please revoke this card. And even if the criminal has stolen it, it's no longer working, right? So it's recoverable states. Change your password, get a new credit card, problem fixed. But with privacy, I can't change my medical data. Like if the hacker learns that I had cancer treatment, I can't change the fact that I had cancer at some point in time, right? I can't take that back. If they learn when my birthday is, I can't change my birthday. They learn my blood type, I can't change my blood type, right? So the privacy breaches are unrecoverable. They are out there forever and there's nothing I can do about it. And security breaches are different. And sometimes we do have both security breaches that result in privacy breaches, right? But privacy breaches are just inherently different in the sense that we don't recover. We don't recover from a privacy breach. Okay, so I want you to remember one thing from the talk. That would be it. Privacy breaches are forever. So now I wanted to try to give some sort of definition, because now I talked about how privacy is so difficult and it can mean so many different things. I wanted to give my attempt at a definition that I think is going to be useful for programming languages setting. So first of all, privacy is about protecting people. It's not about protecting my computer, right? Because we saw all this like right to privacy from 1890, right? Like privacy is something that we wanted before we had computers and digital systems. So privacy is, I think, inherently about us as people and citizens, that we have the right to protect something about us, right? But protecting what exactly, right? And this is where it starts to get very tricky. Because indeed, I think that it depends. It depends not only on what setting we're in, but also who you are, what you think is private and not, right? So we looked at contextual integrity before, right? And we learned that it can be the setting. It can be that, yes, I'm okay with sharing medical information with my doctor, but not with the supermarket. But it might also be that maybe I, as an individual, am more secretive than others. Maybe I think it's very secret what my favorite color is or what my favorite movie is. And some other people are fine with sharing that information. So I think we need a notion of talking about protecting things that are important to that individual. Like we need flexibility in the notion of what is private and what isn't, right? So it's some information, but maybe it's the person themselves that defines what that is. And so my interpretation here is that we want to protect people's behavior, right? And that is something that transcends digital systems. That is something that exists in the wild. Like when we saw the Warren and Brandeis with the paparazzi taking pictures, right? Like the fact that I go and see certain people, right? That's part of my behavior, part of something I do, and something that I would like to be protected. And that sort of makes sense maybe in the physical world, but what does it sort of mean in a digital setting? So, okay, so what is behavior in the first place, right? It can be things I do, things that I think, opinions I have, people I see that, paparazzi might take a picture of, who I like, but also, who I don't like. Maybe this is something that I don't want them to know that I don't like them. Or if I have a crush on someone, maybe I don't want them to know that. And in extension, in digital system, I think protecting people's behavior is all about protecting their data, because this is how our behavior sort of translates into digital systems. It becomes data when we interact with digital systems, right? So the data itself will leak information about our behavior and input. So we need to protect, I think, data at the end of the day. Might be hard to determine what data. Okay, so some observations that I want to sort of point out from this talk and what we're talking about so far about privacy is, so privacy is not about hiding illegal activity. And I can't stress that enough, because there's this whole notion of nothing to hide. And that's usually backed up by the fact that if I don't do anything bad, I don't have to hide it. Because if I don't do anything illegal, I won't get caught, right? But I think that's a complete misinterpretation of what privacy actually is. Because privacy is, not just for criminals. It's also this thing of, what if there is something that I just think is embarrassing that I want to hide? It's not illegal, but it might be something I'm not willing to share. For example, if my favorite movie is something that I think I might get made fun of. Let's say I really like watching Legally Blonde 2, and maybe I don't want to share that with everyone. Maybe I'm scared that someone will, make fun of me for it. Or maybe I think of some embarrassing thing that happened back in school, and I would be embarrassed if that was retold, right? It's not an illegal thing that I did. It's just something that I feel is embarrassing and I don't want it to be shared, right? So privacy is not about hiding illegal activity, right? I would say, and this is coming back to that definition I'm trying to make here, is that privacy is about choice of what to share, right? And that ties into contextual integrity, right? Where you're saying there's an appropriate flow and there's an inappropriate flow, right? It has nothing to do with things being illegal or not. That could be the distinction that you make for you. But ultimately, it's about choice. And this is also something we see in the German justice system, where there's this notion of informational self-determination, which basically says you choose what information you are sharing. And I really like that sort of notion. So privacy is about choice. It's not about, I don't think it's about hiding things. I think it's about determining what to share, okay? And we learned before, right, that privacy breaches cannot be undone. Like diamonds, they are forever. Because we don't unlearn secrets. And these together have this implication that basically we need good defaults that protect our data, by default. Otherwise, this choice of what to share is not possible. So for example, if I log into a system, sometimes there is a setting, the default setting is that, it shares my contacts or it uses my data to train the AI model to do something, right? And if that is the default choice, I actually can't have the choice of whether I share it or not, right? Because the choice has been made by the default. So the default really needs to be conservative. The default needs to be, don't share the data so that I can decide later if I want to share it or not, because I can't unshare it, because we could not unlearn things, right? So we really need good defaults in order for privacy to be possible, because we need to have choice. Okay, so this was how I wanted to reason and define privacy. So privacy is about information flows, and it's about choosing where your information goes, because that is an extension of your behavior. Right, so I told you that the talk is 2 parts, right? So this was the first talk about privacy. So now hopefully you feel a bit more, confident or comfortable talking about privacy, and you kind of understand what I mean when I say privacy. Now, let's talk about why is it a PL problem? So I want to start again making a claim. So I want to say that I think we need PL level defenses to protect behavior, because programming language techniques actually allows us to trace how information flows through programs. And right, I talked about how behavior is ultimately being translated into information and data instead of programs, right? So we need to be able to reason about those flows to be able to determine are they appropriate or inappropriate flows. Right, so if we look at the information flows and we think of programs, if you write programs, you then know exactly what your program looks like, right? But at the end of the day, as citizens or just users, right, like a lot of the time we just interact with some program, we have no idea what's going on inside of there. We might be able to use some techniques to try to reason about it, but a lot of the time you're presented with some program and you run it. You don't actually know what that program does. And this input that you give to the user, to the program, might actually be sensitive information, right? Like there might be some, I go to a website and it will like present me with a quiz and it will tell me what political candidate I should be voting for, right? And I input my user behavior, right? My opinions basically into this program. And how can I know that, you know, the output that's created from that is that still gonna be a privacy violation? And there might be some like side effects. It might start printing some things, or something else might happen, right? So by just looking at the program this way, it's very hard to tell. So basically, I would probably say that, well, everything is potentially tainted by that secret input. But if I do have PL level techniques, we can basically we can take away this sort of opaqueness and look inside of the program, right? And then we could see, aha, these are the actual flows. And in this case, we see that the output is related to the user behavior because that was the input, and the side effects are also related to the input. So probably all of this should be mentioned, right? But we could also have a case where there are side effects that have nothing to do with my input, right? Like if, for example, when the program starts, it always prints hello, then that is not user behavior, right? So that would be safe. And with a programming language sort of level of granularity, we would be able to tell these apart. And I also want to say, beware, even when we look at the inside of a program like this, we can have side channels. For example, timing or energy usage. And I will give you two examples. So with the timing, for example, if your program checks a password, in case you have a naive implementation of a password checker, you would check, first you would get the input password and you have the saved password, right? You will try to compare them. You would just check first, are they the same length? And if they are not, you would just say, no, wrong password, right? And that would be very fast. And then the attacker can just try to make sure that this check takes slightly longer to realize, okay, what's the same length? And then you start, if you want to do it the effective way, you would start comparing character by character, right? Like, is this the correct character? And if it's not, you just say no, right? So this means that the attacker would be able to leak bit by bit, basically, like one character at a time, what password it is, just based on observing differences in timing. So timing can leak a bunch of stuff about the input if we are not careful. And similarly, energy usage. We've actually seen this on encryption algorithms, where the block cipher are very like easy to recognize from some sort of power consumption, and you could actually leak what the cryptographic keys were just by observing how much energy was used. So you need to be very clear, like very close to the actual equipment to do this, but it's possible. So to do this, we would need some more fancy techniques. Yeah, but we could still do this with programming language techniques. I will show you later on. There is an example of how you have compiler support, for example, for timing and so on. But you need to be able to model what's going on in your system, right? And you need to be able to track what are the possible places that your information can go, to determine whether the information flow is appropriate or not, whether it should be considered a privacy breach or not. So this you can do with information flow, and specifically information flow control, which is a technique in in programming languages. Right. So you might say, well, do we really need information flow? Isn't this a bit overkill? It seems a bit paranoid. Well, I'm hoping to convince you by showing you two examples. Maybe relatable examples. Let's see. So the first one is federated learning. So in federated learning, the idea is basically will attempt not to share information, or at least not share all information. So for example, if we have two companies and now they have these two databases over here, one for company 1 and one for company 2, and they want to kind of share some data, but not their actual database with each other. So they want to compute this shared model, like a machine learning model, to do some prediction for them, let's say. So they will take their sensitive data and together they calculate this shared model. But they do this in a distributed fashion, so they never actually share the databases, right? And what this basically is then that we do some distributed computations, which allows us to not share the raw data. And the goal is let's not share the data because we will consider that a privacy breach. But the problem is that if the model is trained on sensitive data, it can also leak sensitive data. So the model doesn't just forget that sensitive data. So what can happen is that this shared model retains some information because it's trained on the sensitive data. It could also start outputting company secrets. So an example here would be like, let's say that this employee from company 1 is using the shared model that is supposed to be privacy preserving, right? Because the data wasn't really shared. And they ask, well, what's the secret ingredient? Let's say that they're making different sodas, right? And the company 1 asks, what's the secret ingredients to making the best selling soda? And then the model responds, cinnamon. And it could be the case here that company 1 doesn't use cinnamon in any one of their soda recipes. But the fact that they're learning that cinnamon is the answer tells them that this must have been learned from company 2. So meanwhile here, company 2 employees is, well, how could my data have been leaked? I never shared the information, right? So federated learning on its own is not enough to prevent these kind of information flows. We would need something stronger to make sure that this doesn't happen. For example, we will need to reason precisely about the information flows. And the second example I wanted to give you is maybe more of a day-to-day example, of encrypted traffic. So let's say that we have Alice and Bob, and they want to exchange some information. Maybe this is instant messaging where there is this centralized server that just forwards messages. And, Alice can send a message to Bob, it gets forwarded by the server. And, it might be the case that we actually have an attacker here. So we do have, if I can get my clicker to work. We have Mallory over there observing the network. And in case that the network traffic is actually encrypted, well, we could be like, well, Mallory doesn't really learn anything, right? What information can she have deduced from this? And, she can't read the message. I might say that's fine, but Mallory does learn something. She actually does learn that, well, Alice talks to Bob. Even when the message is encrypted, this is leaked. And you could use techniques from anonymous communication, such as onion routing, like Tor, and make it more difficult for Mallory to trace who is talking to whom. And you could say, okay, but then I can solve this problem, right, with just using Tor. But it's actually not enough, because it might be that there is information in this underlying protocol, in this case instant messaging, that Mallory could still learn something from. So if Alice has some of her secrets basically on the server, Mallory could just interact with the server and learn some information. And so this is actually the case. We have a paper from last year in EuroSNP where we talk about metadata privacy beyond tunneling. We look at the signal protocol, because here the server knows something about who you're sharing, not who, but they know about your cryptographic keys. And then Mallory, even as an attacker, could start interacting with the server and learn something about Alice. So here, it's actually not enough to just treat the network layer. We would actually need to reason more about what was going on inside of the protocol to figure out if the information flow is good or not. So some observations here. Well, I think really the big thing is that protecting one layer of the network stack, or from the application down to the to the network, if you will, it's not enough. We actually need full stack defenses. So we need to be able to reason precisely about the information flows, because we saw this with Mallory now in the last example, interacting with the server. We had protected the network, but we hadn't protected what was going on in the server. And in the federated learning example, we had created this other model, but we hadn't made sure that there was no flow from the secret data into that model, right? So we need to really, at every layer of what we're doing, make sure that there is a defense. And I think we do that with programming language techniques. So, and this was concluding the second part of the talk, that this is why is it a PL problem. So now I want to basically try to start, putting it together, because now you have all the sort of background information. What are the things we can do then? So if we think of user behavior as being input to programs, then we can use programming languages, as I showed you, right, to track information flows, which basically means we are tracking user behavior as it flows through programming, for programs, for protocols, through digital systems. And this also allows us to recreate this very precise model of who should have access to what information, and in extension, who should not have. So this basically allows us to express things like contextual integrity using information flow control. So it's a fine-grained version of access control, if you will. And here, the data, again, that's created by people, by users. So we can reason about what flows are appropriate and therefore not being privacy violations, and which ones are inappropriate and should be ruled out. So we can use PL for them. And I want to show you some properties. I spoke in the beginning about properties that were common in security. So now I want to add some properties that I think are good for privacy and that we can use PL techniques to reason about. So one property that we do have is non-interference. This is something we really enjoy in information flow control. And this is about preventing information from leaking. So we think of it as, again, different flows. So here we have some private input to some flowing to some private output. And we typically in the literature, we refer to this as high context. So high is the sensitive thing and the thing that we want to hide. And then we have, some public input, some public outputs, and we think of these flows as being labeled low. And this is just because in the literature, this is a lattice where there is some sort of top level, which is high thing, and low, which is like, the bottom, where anything can flow. So if we think of these, we can think of the sort of, non-sensitive information and non-private breaches as low labels. And here we have Mallory, right? So we can think of the attacker Mallory can observe these low flows, but she cannot observe the high flows, and we want to keep it that way, right? Because those are the secrets that we, in this case, want to preserve. So it's okay for low flows to flow into high. For example, let's say that the high flow is my medical data, and the public thing is, we talked about the weather data before, right? So my doctor can write in the journal something that has to do with the weather without being a privacy violation to me. For example, let's say I go to the doctor because I fractured my wrist because I fell on some ice outside because, the weather was, it was a lot of snow and ice, and so I fell. So if anything about that makes it into my medical journal, it's okay. It's not a privacy violation. Nothing bad happened. It might be even relevant. But we don't want the high flows to leak into the lows, right? So I don't want my medical data to be bundled together with this weather data and made available on the weather forecast, right? That would be an inappropriate flow. And in information flow control, we have ways of proving this property of non-interference, where we can say that none of these inappropriate flows were present, right? So this is a nice property that I think should be more prominent in privacy. And then we also have differential privacy, which is actually a property. I promised you before that I would talk about it, so I will say a little bit more about what it is and what it can do. So imagine that we have some data. Again, here is some database. It has this data that we think is very sensitive somehow or very private. We don't want to share it. And so the typical use case of differential privacy is to anonymize data. Basically, what I'm trying to say that in non-interference, we were talking about don't release any of the secret data, right? In differential privacy, we want to release some data. We just want to control how much. And this is typical in when we want to do anonymization, right? Because then we might want to publish some statistics, maybe some averages or something, right? But we don't want to publish data about specific individuals, right? And that is the sort of properties you can get from differential privacy when you want to learn something statistical about the population, but not about any one individual. So let's just denote this data set that I have, the database. It's as X. And then, if I can manage my slides, we will have some query on X, right? And I want to calculate this sort of result. This is the statistics or the information that I want to learn about is Y. But it would be nice if it was not, exactly Y, because I would like for it to not be, a privacy violation. Because maybe if I publish exactly the right answer, it leaks something. Like if I publish the average salary, if I don't know, everyone in this room, which happens to be just me, then I'm publishing my actual salary, right? So I would like to avoid these kind of mistakes and say that it's almost Y, but not really. And so differential privacy actually allows us to capture this. And so what it does is it tells us how close the outputs may be for the same input. And it tells us, how close in the sense of a probability distribution, not exactly what the difference is between these two. So for these two, we are able to say how similar are they, basically. So it's a probabilistic, because I talked about distribution, a probabilistic notion, and it's indistinguishability based, because I'm saying that this Y should be almost the same, right? And so I'm sort of quantifying how similar, and usually we hide that under a variable which we call epsilon. So differential privacy was in the beginning called epsilon indistinguishability. So that's how that sort of works, and it's a property about an algorithm or a property about a program. And this is quite unusual because a lot of the time we will talk of data as having been anonymized, but differential privacy talks about how the process anonymizes the data, if you will. And that means that it's actually not just like this data is private or not, right? This data has been created by an algorithm that is differentially private, and that means that we can reason about it as a hyperproperty. This means that for any input to this program that we prove to be differentially private, those outputs are going to be okay, if you will, and they're going to be receiving this notion of sort of differential privacy, right? Because it's attached to the program rather than the actual data. And so that's actually quite neat. So I was a bit maybe pessimistic earlier, so I'm hoping to give you also some hope here towards the end of the talk. Because I said there were things we can't do. Now I want to say that, okay, now that we have these properties, there's hope. There are things that we can start to do. For example, non-interference, that can be used when we want to ensure secrets are not leaked. So if you remember my examples from before, right, I had this example of encrypted traffic where we could accidentally leak information and we didn't want it. We had Alice and Bob. Now I drew them as looking happy because we have this good property of non-interference working on our side. Now I can define that the messages between Alice to Bob are actually in this high context where I don't want this leakage, right? And I can reason about it and I can prove that this actually holds, right? So now I can formally reason using PL techniques about the fact that nothing was leaked to the wrong person. So Mallory will not learn of this message's existence. So that's a motivating example for using programming language techniques, I hope. And we had this other release example before, in the sense of, here we actually wanted some information to be released. Like, we wanted to calculate some, statistical query, and we didn't want actual non-interference, because then no information is leaking, and it's very useless if I have a statistical database, right? But I'm not allowing you to run any queries on it, because that would be violating non-interference, right? So instead, we can use differential privacy when we do want information to leak, but we want to control how much. So we want to be exact. And that's a feature, not a bug. That's a feature of being able to leak information, right? So in our example with federated learning, what we can do when these companies want to train their shared model, right? They could train this model using an algorithm that's itself is differentially private. And then we could tweak how much information is it able to leak. And it could prevent this company 1 from learning that company 2's secret ingredients is actually cinnamon. Okay, so some other motivating example, because again, I wanna end with hopefulness. I'm not saying that privacy is this like really hard thing. I wanna say privacy is also this really exciting thing where we can use our techniques. So for some of these properties, we do have language support, like programming language support. For example, for information flow control, to reason about non-interference, we have this language just like Jeff, which is a Java-based programmer JS flow based on JavaScript. Leo is this Haskell library. Paragon is a separate programming language, and Troop as well. So you can start using them already today. Most of them are sort of like research languages, but they exist. And we also have language support for differential privacy. So there's Dipala, which I believe is a Haskell library, and there's Fuzz. So this basically means that you can leverage your compiler and have your compiler help you simply through type checking, right? That this program is correct and guarantees differential privacy, or that there is non-interference, right? So that's actually, I think, really exciting to see these properties, possible to apply, and not having to do it all manually every time. There is also a bunch of verification efforts in this sort of line of thinking. So for differential privacy, for example, there's been several papers now, I think, by this point in POPL. And there was this paper in 2021 for deciding accuracy of differential private schemes. I think that the year after, there was deciding the privacy of them, because you have to have this trade-off between privacy and accuracy. But yes, that's a full-on verification effort, doing this on the logic level. And there is, and I think I promised to mention this later, there is this paper from CCS of 22, enforcing fine-grained constant time policies, which was about compiler level support to make sure that there is no difference in timing. Like we talked about this password example of if you manage to if you don't manage to have your functions take the same amount of time, that you would have timing leaks, right? So here is actually compiler side tools for helping you avoid those issues. Non-interference, we also see it in logic when there is support as well, and so on and so forth. Like there's a bunch of things happening in this field, and I'm hoping now, if you're a programming language researcher or just maybe in some other area where you if you have some of your tools that you could start adding and working to help us provide privacy. So please add your ideas here and get excited about privacy. And to help you get started, here is a sort of, if you're a PL researcher, a programming language to privacy dictionary to help you think like a privacy person, or maybe even more so to talk like a privacy person, because sometimes just interfacing with a new field can be a bit different because of terminology. So in PL, you used to say, here's a specification. In privacy, we like to call it a policy. And so basically this is reasoning about who is the attacker and what are the properties that we want to guarantee, right? So this is where we sort of define our threat model as a sort of policy, and this is specification, if you will. when you in PL say implementation, in privacy we usually say mechanism. So what techniques gives the property? For example, we'll talk about different mechanisms that are differentially private, right? And these are just implementations. And lastly, in PL, it's common to say verification, whereas in security or privacy, we tend to say assurance. And this is just how do you prove that the specification is met, right? So this is just some terminology to be using. Okay, so to summarize, I want to say that privacy is an unsolved problem, and I think really there is room for a lot more people in here to help us understand what's happening, because I think privacy is a really important problem. So I think we need more efforts. But some of the difficult parts of why it remains unsolved, right, is that we seem to lack a universal definition of what privacy is. If we will ever be able to come to one, but so there is no clear way of immediately knowing like what is the good definition. Maybe we have different ones for different problems, but it creates a lot of confusion when talking about privacy. Even now, right, I was spending a lot of time in this talk just trying to define to you what do I mean when I say privacy, right? So this is a bit problematic. And I think at this point, it's also problematic that we have these unclear sort of connections between definitions. So I talked about different definitions of privacy, right? Like, so we have differential privacy with this like statistical, rigorous, formal view of privacy as something, we can prove. And then contextual integrity, which is a more overview kind of how, like in the more abstract way of defining privacy as inappropriate and appropriate information flows in certain situations or contexts. And then there's GDPR, right, where privacy is just defined as personal or non-personal data with a very different language from what maybe we're used to saying in maths or in programming languages, right? So it's also difficult to understand how would you combine these. Are they possible to compose and in which way? Like in privacy, we also have this notion of for anonymizing data like k-anonymity or L-diversity and so on and so forth, and it's not clear how these sort of interface with each other. So this lack of a universal way of even expressing privacy or defining what it is problematic. And it's on its own, it's also very difficult, because I told you, right, that privacy is this full stack problem where basically we are protecting these humans, we're protecting people, right? We're protecting people's behavior rather than like protecting a system, which is something that we as the programmers, we have designed and we understand hopefully how it works, right? Here we're sort of trying to interface with actual people and see what happens to that information and how it spreads through systems, right? So there's so many layers that needs to be controlled. And I think we probably think of a computer system that we are defending, and that's part of it. But also on top of it, we have the sort of interaction, the human-computer interaction with, people using our systems. And then in all of this, we also have law and legislations that we need to abide to. So privacy is a really difficult problem. And when we do have privacy breaches, it could be just because we sort of made a mistake on any one of these layers, right? So it's hard. And therefore, I think it's really important that we have more people focusing on these problems and helping us try to solve it or provide some ways forward. And really, that's what I think that the way forward is. It's for getting more people in the field. And so I call this talk the invitation to privacy problems. So I would love for you to accept the invitation and start solving privacy problems. So in the beginning of the talk, I don't know if you noticed, but there was this stick figure extending this gift. And that gift is, of course, privacy problems. So I want to give those privacy problems to you, and I'm hoping that you're receiving this gift, and maybe you're happy about it. So what I want to say is bring your tools from your research, bring the tools that you work with, and think about how can you use them. So how could you define privacy given like the knowledge that you have, and what would be the property you would be expressing privacy as? So really accept the invitation and start solving privacy problems, start talking to privacy people, and maybe together we'll be able to, come up with some better definition, better, properties, and just like being able to actually provide privacy in real systems. So I'm hoping that you'll get excited about that. And with this, I would like to thank you very much for listening to my talk.